Good morning and welcome to today's session, which is on deep reinforcement learning. This is probably one of the more technical sessions, but we'll work through things slowly, and this is done as a video with tutorial notebook, so you can take your time, slow down. You might want to re-watch a couple of sections again to sort of get the feel, particularly around Q, which is a bit fiddly just to begin with, but it'll soon sink in. So today's session is broken up into three parts. There's first of all the tutorial slides at the beginning, where we'll just go through the principles of reinforcement learning, and we'll work through Q, one of the common ways of evaluating what's the best action to take, what you think is the best action to take in any particular circumstances. So that's the first session. The second session will look at a classic control problem where you will see these methods often illustrated. It's a simple, relatively simple problem. It's balancing a stick on a cart, and the agent has control of pushing the cart to the left or pushing the cart to the right. So it can either accelerate the cart in one direction or slow it down and push it back in the other direction. And then we'll show the versatility of this method by taking exactly the same method and replacing the cart with a hospital bed system where the agent has to control the number of staffed beds and try and keep that number right, where there's a delay between making any decision about whether to increase or reduce the bed stock and it actually happening. And there's random arrivals, different numbers arrive each day, and there's a weekly pattern, so there's fewer admissions on a weekend, such like this. So it's got to learn to anticipate those things, and we'll see how it works on that. But it also shows the sort of transferability of these agents, because it will be exactly the same agent taken from one situation to another. Okay, well, let's get going first of all with the tutorial. Okay, we'll start with a higher level view of what reinforcement learning is. You've done some reinforcement learning with the multi-arm bandit problems about how you decide which bandit to work with to try and get the maximum reward. Deep reinforcement learning generally just means it's using a neural network to try and work out what the best action is to take, some kind. Okay, so at a very high level, we have our agent, and here this kind of there's a representation of a neural network in there, and it senses the environment. So it gets observations from an environment. It will decide on what action to take, one of three actions here, and it passes that action to the appropriate place in the environment, and the environment will return a reward and will return a new set of observations because the environment has changed state in some kind, we say. And as we covered in a previous lesson when we looked at the video from Lex Fridman of MIT, the reward structure can be very important and something we need to think through, because the agent is going to try and maximise the reward. But it might choose its own way of doing things. Like somebody asked me the other day when I said, the power of these things, well, could they find a way to get peace in the Middle East? And I said, well, possibly, but it might do it in an unexpected way, like killing everybody in the Middle East, and then there would be peace. And that's an extreme example, but agents will just try and maximise the reward, so the reward structure is really important. Okay. Let's go through some key things about reinforcement learning, some general characteristics that's going to be common to them all. So the first thing is they need to sense the environment in some way. Something to appreciate though is the agent may have incomplete knowledge or sensing of the environment. That's okay. So we have an environment that's got lots of things going on. So that could be a hospital if we're doing healthcare. But the agent may only know certain things about the environment, or it might cost more to get more information about the environment. But it needs to sense something of the environment, otherwise it's just completely blind. The other important thing is there's some component to trial and error search. So this is what we've referred to before as the exploration-exploitation dilemma. That if you always go with what you think is best, that's exploitation. That you know something that might work okay. But if you only ever do that and never explore, then you might be missing a better way of doing things. But exploring comes at a cost as well, in that you might choose a really bad way of doing things. So that's a common theme of how do we maximise our return by getting good exploration, but we sort of want to also minimise the total exploration. We don't want to explore more than we need to. So that's a way to balance our best predicted action, exploitation versus exploration. Now, always in the reinforcement agents we're looking at, what we're trying to do is we're going to try and link in some way the state of the environment at the moment. And the state, we can say, is what can I observe about the environment now? And say, therefore, the action I will take given the current state of the environment is action A. And then that leads to a reward of some kind and a new state. The reward, we frame it as a reward, but it could be negative reward. So it could be the only other thing we get is a negative number if a patient goes over 4 hours in emergency department or something like that. So there's a reward and then there's a new state. We're trying to always predict this. We're trying to be able to say, if I am in state S and I took action A, then I will have ended up in state S prime and I would have received reward R. That's the knowledge that we're trying to build up for all states and all actions. Now, something we can add here is that obviously every state might be completely new in some way, but neural networks like us will tend to look at similarities in the state to something that it's encountered before and be able to say, this state is very similar to what I've known before. Action, whatever it is, was a good action to take, and action B was an appalling action to take. So it will choose the better action. Now, the agent is going to try and maximise long-term rewards, and we can call this our return. And then sometimes that will be, and we want it to be, at the cost of short-term rewards. So the agent isn't just going to act to say, well, what's the best thing I can do today, if it's going to lead to an absolutely disastrous outcome tomorrow. But there is also the sense that today is actually a bit more important than tomorrow, which we'll come back to. But you can adjust that balance. Now, we accept there is some uncertainty in linking action to reward. We might, for example, think that a particular action, well, let's take, if we're in a car, we might say turn left, but maybe we hit a block of ice and we actually turn right. And the agents are designed to sort of cope with that uncertainty of action. Or if we've got an agent that's making recommendations in a clinical setting what to do, then the human might completely ignore that recommendation and take another action, or it ends up in another state. And our observations might also be inaccurate as well at any one time. So the things we're looking at cope with the uncertainty. Observations might be inaccurate, and action may not lead to the expected state. And the final principle is that what we're expecting is that learning leads to improved choice of actions. And the choice of action in any particular state is called the policy. sometimes you'll see that put as pi. So learning, it takes time, and that's an important thing to realise, but we're looking for constant improvement over time. Okay, elements of reinforcement learning. So some nomenclature which is common across a lot of methods. So the environment is all the observable and unobservable information that might be relevant to us. So most of the time, if we're working in the computer simulation world, the environment is a simulation. But it might contain things in it that are required for the simulation, and the environment has that information in it, but that information is never passed to the agent. And so there are things that the agent will never know or see, and will have to try and kind of work out about the environment. So the environment is everything, and then we've got the observation, which is what can we sense from the environment, and accepting that sometimes it's imperfect. So then we talk about a state, and a state is the perceived or perceivable environment, and sometimes state and observation are used in pretty much the same way. So observation and state you may see used interchangeably. Then we have our actions, and so the actions may be discrete, so turn left, turn right, increase bed stocks by a given amount, say 5 or 10, those are discrete. Or it can be continuous, so that might be an accelerator pedal, or we might give the agent free range to sort of say, well, you can add anywhere between 1 and 1,000 beds or something like that. It's worth mentioning that because different methods work with different, whether it's discrete or continuous. In an ideal world, they'd be the same methods, but they're actually a little bit different. Then we have our policy, pi, which we've said is, well, policy is what action we decide to take given our observations. Then reward, and we have a reward signal every time we take a step in the environment. So we get back observations, which is our new state, and our reward. Now, a lot of methods will build up a memory, and we'll be using that this morning, and it's a database of what state you were in, what action did you take, what reward did you get, and what new state happened when you took that action. And we build up that memory, and we might vary the size of that memory. Okay, so here we're just coming on to 3 definitions of words around judging how good things are. Now, value refers to a particular state. How good a state is that likely to be? So if we were playing chess, the value is some way of calculating the value of the board. So that might be, for example, you score pawns 1 and queens 10 and the other pieces in between, and you add them all up. It would be a very, very crude way of scoring a chessboard, which you can do in methods like this. Or in emergency department, the value might be I've got very little queuing in the emergency department at the moment. So value is linked to a state. Q is always linked to an action. And Q is the prediction of what's likely to be the best possible long-term return that I can get for any particular action. And there's this idea that also the value of rewards is what we call discounted over time. So the value of something, a good outcome tomorrow, is still good, but it's less than a good outcome today. And so we what's called discount the value of our rewards over time, and you'll see, and we'll use this term, discount rate is symbolized as gamma, which we'll come back to, which is how how quickly you don't care about rewards in the future. So how short term do you want to be versus how long term. Then we sometimes see the word advantage used, and the advantage is the difference between different actions. So it's very similar to Q, except Q is the actual value of an action. Advantage talks about, well, there are two different actions I can take here. One appears to have a Q of 12 and the other one has a Q of 10. So we talk about one of them having an advantage of 2 over the other one, which has an advantage of 0. So it's a comparison of how good different actions are, which kind of ignore the total value of Q. And then we'll come on to targets. Now you'll see targets used quite a lot in the description of these things. And very frequently, it's not what you're trying to get to, it's the value that we wish to update our network to predict. So if we're doing a classification problem in machine learning, which you will have done by now with the Titanic, we wish to update our network to try and predict a label of a given set of examples that we had. So our target in a classification problem is our label that we think it ought to predict. The target in a reinforcement learning problem is what we think the network should predict as the right value of Q. The problem is it's got to find this out, so it's kind of got to, we'll come on to, it's got to kind of pull itself up by its own bootstraps, because it doesn't know Q until sort of explored, and yet is trying to predict it at the same time. It can get a bit head spinning, and I think some people have said the most remarkable thing about deep reinforcement learning is that it actually works, because there's some things in it that you think, goodness me, well, we'll come on to that. Okay, so here's our high-level view again. We have our agent here, our environment on the right. The agent observes the environment, it gets the observed state, which will be a set of observations about the environment. It then, within itself, has a policy that given a particular state, it will decide on a particular action. It takes that action and then passes that action to the environment and returns back a reward and an observed state. So every step it's taking, it's going through these. I was in state S, I took action A, I landed in state S prime, and I received reward R, until I reached what we call a terminal state. Which is either I want to run a model for 200 days or whatever, or if it's game playing you're doing, it's the end of a game, you've reached the terminal. So we've got state, action, state prime, reward. And our memory is going to be a store of all of those. And that's where we're going to build our learning from in these methods. We've built up a memory of what state was I in, what action did I take, what reward did I get, what was the next state observations, and was it a terminal state. And terminal might be good or bad, or it might not exist. It might be that you're in an environment that will run for forever, in which case we still store terminal because it's part of the common framework, but it will always be 0. So that our memory is built up of those, and so we can put each of those in what we call a vector. So it's a Python list, if you like, of those things. Okay, this gets just a little bit fiddly, or we're going to do some very simple maths, but it is simple. It's just there's a lot of repeats to it, which you'll see. So if you haven't already had a coffee, have some coffee, quite strong, I recommend, and we'll get going on Q. Take this slowly. Pause think through as we go along, because Q is central and to the methods we're using, and want you to have at least a good intuition of it. So Q is the expected, what's the best reward we can get from any particular action from a given state. So it involves not only the reward we're going to get immediately, but from that point, what's the best action, what's the best reward we can get from there. And you might be able to see already, this kind of is an infinite regression of steps of well, the reward that you can get from the next step depends on the best action it can get, best reward it can get from the following step. But we'll work through a simple example first of all. So it's expecting maximum long-term reward. So we want to, the principle is we want to involve some notion of what's the reward I get now, but also what reward will I get from that new state. So an example, let's imagine a game. The game makes it sound a bit more exciting than it actually is, where I have to make just 3 choices between 2 alternative options. So I can choose action 1, I can choose action 2, and I'm going to do that 3 times. And with each choice, I'm going to get a reward. But each choice leads me down an alternative path. And we can represent all these choices and paths in a network graph. So this network graph is 3 choices, each of 2 alternatives. So I'm going to start in state 1. Now from state 1, I can take action 1 or action 2. Now action 1 will lead me to state 2. You see I've got no rewards at the moment here, we'll put that on next. And from state 2 I can take action 1 or action 2, and that will lead me to state S4 or S5. Whereas if I'd gone down action 2 to begin with, I ended up in state S3, and then my 2 possible actions, action 1 or action 2, so this could be turn left or right, whatever, go up, go down, speed up, slow down, will lead me to 2 new states, S6 and S7. So the state that I'm in after 2 choices depends on both of those choices, depends on the choice I made at stage 1 and the choice I made at stage 2. And then stage 3, here I've got some of the choices leading to the same states. So it could be that each again just carries on dividing out, but here I've got a network graph where from state S4 and state S5 I can get back to the same state, though with different actions between the 2. So, and you can imagine, you know, if you're walking around an area that's sort of choices of left or right you can take, at times they're going to lead, different series of choices will lead you back to the same point, and that's what's happening here. And then from my 3rd choice, sorry, this is choice 1, choice 2, choice 3, and then finally all of those states are going to lead to the terminal state. And so there's only one action you can take from this. After we've made our final choice, we get to our terminal state T. Okay, so pause if you need to and just think through. I was in state 1, I took action 1, I ended up in state 2. Or I was in state 1, I took action 2 and ended up state 3. And just have a look at the different ways that you might go through this representation, because it's a small example, we can represent everything in a graph here. Pause, have a look. I'm going to have coffee. Okay, let's put some rewards on. So this is the same graph as before, except now I've got rewards that I get. So if I'm in state 1, for example, if I take action 1, I get reward 2, and then that leads to state 2. Whereas if I took action 2, I'd get a reward of 1, leading to state 3. And so forth all the way through. So there are different rewards depending on the different actions I take from different places. And then finally, I've put action 1 and action 2 here to keep the nomenclature kind of constant throughout. So we've always got actions. And it all ends with a reward of 1 in the final step to get to the terminal. But up to there, all the rewards are dependent on our choices. And the aim of this game, exciting as it is to find the path through that you think is going to lead to the best long-term reward. And from here we can start to use our standard, what will become our new standard nomenclature for reinforcement learning, that we have a state, we have an action, we have a reward, and we have a new state. Those 4 things, and we have a vector, or a list of them all. Good. The order might be different, but it's going to be those four things. Right. Now, this is the bit that's just a little bit mathsy, but the maths you'll see is not hard. It's a simple sum, and that's the beauty of this. This is called the Bellman equation. And the Bellman equation formalizes what we have said previously, that the Q value for any particular state and action, and Q is always about what action you take, but from a particular state, equals the reward, the immediate reward that we get, plus the discounted rate, so of the maximum Q that we can get in the next step. So today's reward is important. Tomorrow's, all the long-term rewards are important, but they are discounted a bit. And typically the discount would normally perhaps be somewhere between, we'd use 0.9 to 0.99. So they're just sort of common discounts to use. So we'll work through this and calculate it. But again, it's this notion that the value that we can get is dependent on the immediate reward, but we also care about the long-term reward. And this long-term reward is thinking through the future of however many steps you can take, and that's what we've got to discover. What's handy, what's beautiful about the Bellman equation is we can quickly build up our knowledge of Q by a very simple calculation based simply on looking at the current step and the next step. That, even though this max Q involves paths of actions well into the future, our calculation at any one time is really simple. It's just the reward plus a constant, gamma, often say 0.95, multiplied by what we think is our long-term best action, best reward from that we can take. We'll come back to that, because to begin with we don't know it. We've got to find it out. So that's the Bellman equation, and that's as mathsy as Q gets, except we'll see now it kind of, because we've got these chain of events, that's where it starts to build up a bit more complexity. The equation's very simple. It's reward plus a constant multiplied by the estimate of our Q, our best estimate of Q at the next step. Okay, let's work through an example. So this example is the graph that we had before. So we have 3 choices, 2 actions each. Now, in a simple system like this, we can calculate everything, and it's best to do it through the terminal state, t, backwards. At the terminal state, there's no possibility of further reward. So Q is simply the reward we can get getting to the terminal state, which is always 1 here. Whatever action we take, the reward is 1. So this could seem a bit odd, because if you're playing a game like chess, then winning, the Q value when you get close to winning is actually quite low, because there's not that much value left to have unless you're putting all of the value on the terminal state. But a lot of methods might place value in taking queens or rooks or whatever throughout the game. Our value is going to be highest at the beginning and lowest at the end. And one way of thinking of that is what are our lifetime earning potentials? And for those of us in our 50s, our maximum lifetime reward that we can get now is considerably lower than anybody in their 20s, because we can only work for another 10 years or so, or well, I don't know, knowing this government, we're probably working for another 30 years. But anyway, we're limited in the amount of time we can work. So our value, Q value, is lower, whereas somebody at the beginning of the career has all the potential to earn vast amounts of money and be the next Elon Musk or Jeff Bezos. We could do with more Elon Musks than Jeff Bezos, I think, but anyway. So S8 to S12, we're just going to follow one path down here. That's got T has no value in itself because it can gain no further reward. So the value of S8, our action, is going to simply be 1, which is our reward. So S8, we can say our Q of S8 is 1. Now, taking action 1 from state S4, we're heading backwards, comes with a reward of 1. Now we know, in this example, we know S8 has a Q of 1. So if we use a gamma here of 0.9, the Q of S4 is the immediate reward 1 plus gamma multiplied by the Q of S8. And the Q of S8 is 1, so the Q of taking any action from S8 is 1. So the Q of action 1 from S4 is the immediate reward 1 plus gamma 0.9 times the Q of S8, which is 1. So that leads to a total value of 1.9. So the value of action 1 from S4, the Q value, is 1.9. Now, taking action S2, taking action 2 from state S4, so in the same state, leads to state S9 with a reward of 2. So, to calculate the Q of action 2 here, we have the reward 2 plus again gamma multiplied by the Q of state, the Q of the best action of state from state 9, which is again 1 because everything's 1 down here. So the reward, so the Q value of S4 and A2 is 2 plus gamma 0.9 times the Q of S9, which is 1. So we have a Q of action 2 of 2.9. So we've got 1.9 if we take action 1 2.9 if we take action 2. So we now know the best possible queue from state S4 is 2.9. So let's carry on working back. Let's look at from state 2, action 1. So that's going to lead to a state S4. We've already calculated the queue for state S4. It has two possible queue values depending on the actions. 1.9 if we took action 1, 2.9 if we took action 2. So the best is 2.9. And that's what we're looking for in the Bellman equation. What's the maximum queue of the next state action pair? So now for state S2 to S4, our reward is 3 plus 0.9, our gamma, times 2.9, which is our best action from state S4. So the queue of state S2 and action 1 is 3, the immediate reward, plus gamma 0.9 times 2.9, 5.61. And you might be able to see that the rewards we're getting here are slowly being eroded as we go back by repeated use of gamma. So this reward effectively is multiplied by 0.9 in this step and is multiplied by 0.9 again as we go through this step. So the further into the future the rewards are, the more they get eroded by gamma. But at any one time, our equation is simply this, which is our immediate reward plus gamma times the max Q of the next one. Okay. So, if you're feeling brave, can you work out, starting at the end and repeating the sequence that we did, the Q values for each state action pair in that network graph? So you always want to have, in this method, have wanted to have calculated all the Qs of the choices you can make afterwards. So start from the end and work back through the network. See if you can do that. It's a good exercise if you can. Okay, so here are the answers. If we set a gamma of 9, what I've got here is the working backwards. I calculated Q for each of the steps, so the last four they're always 1. Then for each action you look at the best Q of the next step and you calculate a new Q based on its own reward plus gamma of the best Q of the next step. So that's exactly what we worked through before, and this is just working through it from the beginning. And we can see here, this is what I mentioned, that the Q values are actually highest at the beginning in this sort of scenario where we have a terminal state than at the end, because we've got maximum potential at the beginning and least potential at the end. Now, an agent will simply come along and take, well, if it's doing exploitation rather than exploration, if it wants to take what's the best, it will look at state and it will look at the two actions 1 and 2 and it will see which value is highest and go down that route. So from state 1 it will take action 1 because it has the highest Q. So that leads to state S2. Now state S2, action 1 and action 2, the value of Q is highest for action 2. So it will take that one. But this is worth noting that at this point the agent has decided to take an action with lower immediate reward. So state 2 would have given it a higher immediate reward, but action 1 would give it a higher immediate reward, but action 2 leads it down a path that it can get to an even greater reward. So following Q rather than following what's the best value of the next action takes us down a path that maximizes the reward we can get. And so from there, so you would go from state 2, you would go to take action 2 state S5. From state S5 you take action 2, this gets us the big reward and we end up in state S10, and state S10 leads to the terminal state. So if we have a look back up here, the path we took was action 1, then we ignored this higher reward here and went down this path here. We took a lower reward for action 2, but that took us to a state where we could get a bigger reward, action 2, and through the terminal. We could have also got a big reward going this bottom route here, but we would have missed out on a reward of 2. Otherwise it would be the same. So the best route is S1 to S2 to S5 to S10. Okay. Okay, so that's an example, a small example, where we could calculate the queue of everything, and we could find the queue of everything. But in more complex situations, we have a couple of problems to overcome. The first is that we don't see the whole picture all at once. We discover it as we explore and go along. So we can't definitively calculate it in the way we've done. And the second issue is we may actually never see all possibilities. So there is no finite table to fill in, or that we can ever explore. So what we're doing when we can't explore everything is we're tending to look for similarities between the state I'm in now and similar states before. We'll never be in exactly the same state 2 days running, say in an emergency department. It's always going to be subtly different, but there will be similar states that we can be in. Right, so how do we deal with this problem with it in a network? And again, we'll work through an example. This is the bit that, it has been said, the miracle is that it works at all. I think everybody's sort of surprised that this works, because we've got to pull ourselves up by our own bootstraps, that you'll see. Now, we're going to update queue in a network by looking back at a memory. And there's a couple of reasons for that. Though a key one we'll mention at this point is it stops your actions being modified too much by just what's happening to you at the moment, which is if you didn't sample from a memory, you would update what you're deciding will happen just largely based on what's happening now. And we want to take a more kind of stable long-term view from that. So rather than updating on exactly what's happening now, we're always going to go back into our memory and be constantly sampling from that and updating our network based on historic events rather than what's immediately happening around us and what reward we've just got. Now we're going to update queue based on the reward, as we saw before, and the queue of the next step. So when we update our network, it's just as before. We only need to look one step ahead, and we're going to say, what's the best value we think we can get from that step, and update our current queue value. So this is what's called temporal difference learning. Sort of what do I think the next step will be, and use that to update the value that I've got now. Now here's the odd thing and the surprising thing of why it works, in that you're basing your update of your network on a predicted value from the same network for the queue of the next step. So I'm updating myself based on a prediction that I'm making myself. And this is remarkable that it works. The new information that's coming in is any reward I've got now. That's clear and known. That's definitely new, because I'm basing it based on the reward I get plus gamma multiplied by the Q value of the next step. The Q value of the next step is as I predict it to be. So I'm updating myself based on, partly on a prediction that I'm giving. It's a bit odd, but surprisingly it works, though there are problems with it which we'll come across. So it's not perfect, but basically it does work. But as you'd expect, the performance of the network is especially poor early on, because its predictions are the best. Its predictions of Q from different actions are pretty appalling, and therefore the best action that it thinks is also going to be generally an appalling choice. So to begin with, we want to have some kind of exploration, and the method we'll look at today just uses random exploration. Epsilon greedy, which you've been through with the bandits, that there's a chance that you then just take a random action rather than what you think might be the best, and that helps you make sure you're exploring the options. And then it's as your improvements of Q prediction improve over time, you'll more commonly rely on those predictions to make the best action. So more experience you collect, more training iterations are performed, predicted Q, what I think Q is, will become close to actual Q, and I can rely on the network more. There's a note here, when we're dredging into our memory, one of the tricks we can use, we won't use today, but it's something you'll see, is something called prioritized experience replay. And it basically just means train most on where I got my predictions most wrong. So learn more from your mistakes, if you like. There's less value in updating your network with something that it got right anyway. So update it more commonly with things that it got Q value significantly wrong. Okay, here's an example in a network. Now we start with no idea of what Q is. So we're going to set them all, I'll correct that spelling mistake, to 0 to begin with, to make it see what's going on. But a neural network, actually zeros are no good, because you can never decide which is better and which is sort of worse. So networks always start with a random number in them rather than setting it to all zeros. And then from that random number it slowly refines to get better values. So we've got no idea what Q is, and we're going to take exactly the example we looked at before. So as I mentioned, this is called Bootstrapping Technique, and it's amazing it works, because the network is providing the target value for the Q of the next step, and I'm updating myself based on my own predicted values. It's bonkers, it's completely mad, but it works. So here we are. I might have partly explored, or I might have explored more, but the first thing I sample out of my memory when I'm shaping my network is state S4. I took action 1 and I got a reward 1, and I ended up in state S8. Now I've got no knowledge of S8 at the moment, so I'm going to say, well, I don't know, it's Q, so I'm going to assume it's 0 to begin with. So I now say state Q for S1, so action action 1 from state 4 is just the reward 1. So it misses out all the potential reward that's to come. So this is why, to begin with, this is wrong to begin with. Well, it's partly wrong because it's getting some information in there. I guess that's the key thing. So I do that. Then, just by luck for this example, the second thing I sample from my memory is that I was in state S2, I took action 1, I ended up in state S4, and I got a reward of 3. Now, state S4, the only thing I know about state S4 is this top line, which has a Q of 1, because our Q is the same as our reward, because we didn't have anything else to add to it. So, S2, the Q of this path here, I'm now going to set to the reward, 3, plus the maximum Q that's available from S4. The only one I know is action 1, which has got a Q of 1. So I'm going to set my Q for S2 action 1 to 3.95. Oh, here I've used a gamma of 0.95, so that's a bit different to before. So I'm starting to build up some knowledge of incomplete knowledge of value within this network, but it's partial. So carrying on, you just repeat that bootstrapping. And so not early on, the Q network predictions are poor because they don't contain many of the other paths that could lead through down to contribute towards Q. So that's when you perform a large number of random actions, and you're storing up your memory. And then typically we start to hit the memory when we've decided to start training the network. We hit it quite hard. We actually, for each action we take, we'll commonly take 3 or 5 memories and update our neural network each time on 3 to 5 memories for each action we take. So this is going to we hope, build up the knowledge in the network. As the knowledge in the network improves, we take actions less frequently that are completely random. We trust the network more and hope that leads to it. There are some more intelligent ways of choosing between exploration and exploitation. So exploration, choosing random actions; exploitation, taking the best action. We can do things like monitor. We can intelligently change the probability of taking random actions depending on how well that's leading to better rewards. And when our network starts to produce, when relying on the network starts to produce better rewards, that's the point that it will start to tune down the random actions. Okay. Right, let's start to turn some of this into a framework for what we're actually going to code. And going to talk through this, and then we'll have a diagram of it as well, and then we'll go through the code. So hopefully it will all start to sink in. So I'm assuming you've done the Advanced Machine Learning Introduction to Neural Networks with prediction in the Titanic here. So we set up a network, and our network's job is to predict Q for each of the possible actions from a particular state S. So we give it state S, so that's our input features X, and our output Y is predicted Q for each possible action. So if we have 2 actions, we'll have 2 Q values. If we have 5 actions, 5 Q values. In that regard, it's very similar to a standard neural net. In fact, it is a standard neural network. The trick is that we've got to overcome, or the problem we've got to overcome, find a trick for it, is that unlike Titanic, we don't have a whole lot of labelled data that we can use to sort of say, well, this is what you should have produced, and the network has, you've got an error, a loss between what you did say and what our label data is, and update the network to minimize that error. So that's what we've got to overcome. But the actual neural net structure is very simple. Basically, it's because it's a straight regression problem. We're trying to predict continuous value Q for each action. We'll look at the structure of the network in a bit, but that bit is straightforward if you've done the Titanic. So we initiate our network with random numbers rather than the sort of zeros we had earlier. Networks have got to have some weights in them to begin with. We always start with random weights in networks. Then, as I said before, to begin with, because our network is so poor, we make purely random choices to begin with. We accumulate a memory of however many, 1,000, 10,000 action steps, something like that, that come from random actions. And then we start training our network, and we slowly reduce the probability of selecting a random action, so that's the exploration, and we choose what we think is our best action from the network, exploitation. And we might put that as argmax Q of state action. So max Q of state action would mean what's the maximum Q value I can get for my current state with all the different actions. Argmax just means, so you'll see this around the place, just means the index of that value. So if I had 3 actions and 3 predicted Q values of 10, 100 and 5, the max value is 100. The argmax is the index position, so this is the second value, which remember Python starts counting at 0, so argmax would be 1, which is our second value, is the highest Q. So argmax is just what's the index of your highest value. So then we execute our action A, whether it's a random action or chosen for our network, and then we get our reward R, and we get a set of observations of our next state S prime. And we store all of that in memory. What state we're in, what action did we take, what was the reward, what state observations did we get, S prime, where we ended up. All that goes into memory. Then when we start training, we sample randomly from the memory, unless we use this prioritized of sampling more where your predictions are wrong. But today we'll just be using random sampling from the memory. And then we're going to update our network based on that. So for every transition we sample from the memory, we calculate a target Q. Now this replaces our normal label in more classically supervised neural networks, so either regression or classification. We have a whole lot of label data. Here we don't have a label data, so we have to create our label, if you like, our target Q. And so this is the bit that can seem a bit mad, because our target Q comes from our reward. Now that's good, that's real, that's hard numbers coming in. But then we get our max Q, what's the best action from, best Q value available from S prime, from our own network. So this is where we updating our network based partly on predictions from our own network. But we are introducing this firm information R, and that's what we're going to rely on to start to build up, because all Qs in the end are built up from observed Rs. So that's our target Q. Then we get our network prediction of what it would say is the Q of state, our current state and action, and we update that state action pair Q value by minimizing the loss between our predicted Q for our state action and our target Q for our state action. And we never completely correct it. Remember, we have a learning rate which always just nudges networks in a little bit towards our target value each time. And so if we re-hit the network and said, okay, give me the current queue of state action again, it would be a little bit closer towards our target queue, but only a little bit. And then we keep repeating that. So it repeats, keep taking actions, getting rewards and observations in the new state, putting it in memory, don't using it immediately. So we're always training from historic data, and we can adjust the length of the memory if we're worried about historic data becoming too out of date too quickly. We just have a shorter memory, smaller memory. And then keep updating the network. Now that's the basic DQ network. Unfortunately, it doesn't work very well. It'd be nice if we could keep, because this is reasonably complicated already, it would be nice if we could keep it at that for our first demonstration. But networks trained in this way are just too unstable. And a trick is used to help improve stability. They can still be a bit unstable with this method, but it improves it. And the trick we're going to use is here. Well, let's look at what we're going to change. Our target queue came from the reward we sampled and the predicted maximum queue of S primed, which we got from the network that we are updating. The trick is we're going to separate things a little bit. We're going to have a second network that predicts the Q value for S prime. Now that second network we're going to call the target network. The target network provides the Q of the S prime. And then our current Q, remember, is the Q of best Q of S prime multiplied by gamma, our discount rate, and then adding our reward. So our reward comes from memory, and then gamma is fixed, and max Q is now going to come from our target network. Now that target network is just a copy of the network we've been talking about here. The network we're going to use to make decisions, we're going to call our policy network. So we always, when we're making a decisions, hit our policy network. And our policy network is what we update in trading. But we've got this second network, the target network. Now the target network is a copy of the policy network, but it's copied across just every, say, 1,000 steps. So our policy network and target network is kind of like an outdated version of our policy network, but it's stable, and we're not trying to update our estimation of Q in our policy network and the target Q at the same time, and decoupling those two things is enough to bring sufficient stability to make this method work. So what we do, and it sounds more complicated than it is really. Okay, you might have noticed a couple of words just magically changed there to hopefully make this clearer. So double DQN. Now, so we've got two networks, and we're going to use one to predict the best action to take and the other to predict the queue of further actions. Now the policy network is what we've talked about so far. If we only had one network, we might call it the policy network anyway. And it decides the action when playing the game. Now when training the network, let me just go back up a slide. We have this notion that we've got our reward and we're going to take the best Q for the next state, the action that leads to the best queue from S prime. Now, that value we are going to get from the target network. To add just a slight extra confusion, we're going to use the policy network to decide which action we think from S prime has the highest queue, so that will then give the queue for or the max queue from S prime. So we use the policy network to say, okay, I'm in S prime, what queue can I get from here? Because that's what's being used to update in the Bellman equation. If I get to the next step, what's the best value there? We're going to use the policy network to decide which action leads to the best queue, but then we actually get the target value of that queue from our target network. So when training, the best best predicted queue for S prime is taken from the policy network. But when we update the policy network, we get the predicted queue for that next state from the target network. And that target network is basically a copy of the policy network, but we only update it infrequently. So this is decoupling training of our current idea of queue and our target idea of queue. And it seems a bit odd that we're actually using a value of queue for the next state, which we know is out of date. So then we copy our policy network across. You'll see in the code, every so often steps, we just copy one network across to the other. We copy all of its weights across, so it becomes an identical copy, but they're kept separately. And it's called a target network because it provides the target for updating our current network, just as labels or observed values provide the target for a supervised learning network. Okay, so let's look at that as a diagram, and then the next portion of the day we'll start to look at this in the real world. So we train our policy network every single game step, and we've got a memory, and in our memory we have what state we're in, what action was taken, what the reward was, and S prime is the state that we went into, and T is, was it a terminal state or not. And we'll use between 1 and 10 samples per training step. So we get that from the network. Then the target network, when we decide on an action, we get the best queue for the next state from the target network. Then we update our policy network we got a target queue now is the value of max queue for our state action from the target network, multiply that by our discount rate, and then add in our reward. So that's our Bellman equation. And that gives us a new value of queue for state of action. So that's what we're trying to predict. We're in state S and we want to know what is the queue for each action. We just update the action we took from state S based on this Bellman equation, reward plus predicting the best queue from the next state using our target network. And then we update our policy network based on our target queue. So that's replacing our label. And then every, say, 1,000 steps, we copy the policy network across to the target network. And technically what we'll do is copy weights. Okay, so that is the principle that we're going to go through, and we'll go straight into using this double DQ network rather than without the target network. So we'll have an example that should work pretty well from the go. Okay, so have a break and then come back and we will look at a real world example of this. First of all, using a classic control problem, the CartPole, the wobbly stick on a cart that we've got to keep upright. Okay, I'll see you in a bit. Okay, so moving on now to our CartPole example as our first reinforcement learning example. I'm going to set up our environment locally. There's two reasons why this is best done locally rather than trying to run this on Colab or on Binder. The first is that we're using PyTorch, which Colab has been a bit unreliable for in the past, so it may or may not work, but wanted to work, let's run this locally. Binder is just too slow as well at this. And then secondly, this environment with the CartPole, there's some animation around the CartPole moving, that won't work on a remote server. You need to run it locally. So let's build our environment. If you're in Windows, then you will open Anaconda command prompt once you've downloaded the Git repository with all the files in, including the environment setup file. And so if you're in Mac or Linux, more likely to be Mac, but it's going to look the same as Linux. You open up a normal terminal. So here we're in a normal terminal in Linux. Mac will be the same. It should look very similar to this if you are using Anaconda command prompt. Then you just need to navigate to wherever you saved the repository that you downloaded. So save the repository, unzip it, move it to wherever, or you can leave it in downloads. And then you're going to want to navigate to it. So I know mine is in, I put it in a Dropbox, current projects, 2011. Okay. I don't know if Mac is the same, but on Linux, if you double tab, it gives you alternative completions, because I've got two projects starting with 2011 and I want the reinforcement learning. So I've moved now into that folder. So if I look, the contents of that folder, ls on Mac, dir on Windows, I should see my environment.yaml file. So let's just remind you what that file looks like. So it gives it a name, RL. It gives it channels to pick up packages from. I'm just using defaults. Then it's got the packages we want to install, and the ones we're most interested in really is sort of PyTorch for the neural network and Jim for CartPole, and we've also got SymPy, which will have the whole hospital model. We'll use SymPy. So that's just what it looks like. You don't need to look at that. Less is a command in Linux, and it's probably there in Mac as well for looking at contents of text files one page at a time. It was copied from a program called More, where you could look at more one page at a time or extra lines, except in Linux, and I think Mac now it'd be called less, because less is more. Anyway, that's a diversion. So we're going to install our environment. So conda env create, and then we have -f for from file, and then it's going to be created from environment.yaml. I tab completed after the en because it knows it's it's looking for that, and then I hit enter, and because I've got all of these packages previously installed, it doesn't have to go and fetch them and download them again, so this will be reasonably quick for me, maybe longer for you, but I'll pause it anyway while it's downloading. Okay, that's pretty instant actually. And then it tells us to activate the environment, use conda activate RL, which is just what the environment's called, RL for reinforcement learning, and then deactivate. So the two ways I can get into it, I can either type conda activate RL, and then I can open a Jupyter lab from here, Jupyter lab, which is the way I would normally do it. But now, if you use Anaconda Navigator, we should find that environment now present in there as well. So let's have a quick look. So we can list our environments under. So on the left hand column there, I clicked on environments, and this lists all of our environments, and we can see we've got RL there, and it will tell us what packages are in it. But to actually use that environment, I would go back to home, and then applications on, oh, it's already picked that up on RL. So, but you can select your environments to use here, and then I would open Notebook if I wanted to do it from here. Let's do it from here. Okay, so that is, well, let's then find, and it's wherever you saved the files. So I know I'm in Dropbox, current projects. No, not that one. Where are we? HSMA Reinforcement Learning. Okay. And we're going to look at CartPole Basics notebook. I just noticed I opened up Jupyter Notebooks rather than Jupyter Lab. They're very similar. Jupyter Lab's just got some more useful features. Okay, so pause there. You get your environment set up, and then we'll come back and we'll look at CartPole. Okay, so CartPole is one of many environments from OpenAI Gym. So if I just Google OpenAI Gym, and they describe it as a toolkit for developing and comparing reinforcement learning algorithms. And it's a whole lot of different environments, a lot of games, a lot trying to help strange creatures learn how to walk. And this is actually CartPole. It's a pole sliding up and down, or left to right, and the pole at the top is constantly wanting to fall either left or right. It's an inverted pendulum. We'll have a look at that. It's a simple control problem, so it's one of the simple problems. To keep the pole upright, you need to keep on pushing the cart either left or right so that it keeps the pole from falling over. So I'm going to open CartPole Basics, and we'll just have a look. We'll have a look at CartPole, and we'll have a look at one method which isn't reinforcement learning. So there's a bit about the environment here. So I'm going to load libraries. If you have if you're getting errors displaying, then you just won't be able to sort of see the pole move left and right. Change render equals true to render equals false. But hopefully if you're running it locally, you will be able to see it. So let's just start off with, well, we just randomly poke the cart left or right. So we've got a function for random choice. We pass it the environment observations just to be consistent, but it's going to return a random integer between 0 and 1, and that comes from the Python random library. So now let's see what it does. So environment equals Jim. We've imported Jim make, and then give it this name, and it knows to make the CartPole environment. And then what it's going to do, it's going to run 10 times, and it resets the reward each time. It resets the environments. That's the first thing we always do with the Jim environment. We reset it, and that gives us our first set of observations about the environment. Then it's going to it can go up to 200 steps of poking left and right. So we've got for step in range 200, and then if you are displaying it, so try this first, if it doesn't work, then reset or set the render to false. Env should display it on the screen, we'll see in a second. Then we select our action, so now our action is just coming from a random choice. In the future that will be from our DQ network. And then we pass our action to the environment using the environment step method. And that always returns in this order: observations, which is the new state, S prime. So we're starting now to sort of see where the framework we were talking about before fits in. Obs is S prime, we've got our reward R. Done is whether it's a terminal state or not. Basically, CartPole will end if it goes more than 15 degrees off the vertical, then you've lost. And info will be empty here. It's an optional dictionary that environments can pass back, but there'll be nothing in it for this. So equals env step action. Then we track our episode reward by adding the current reward, which with CartPole is always 1. The reward is always 1 while you carry on going. So our total reward will be just the number of steps before it fell over. Then if done, which is the terminal state, the pole has fallen over, break this for loop. Don't try and carry on for the rest of the 200. And then add our episode reward, which is the total of steps before it fell over, or if we got to 200, to our totals, which is a list of all of our results, and then close the environment at the end, which you need to do if it's displaying it, otherwise the display will hang there. And then it's going to print, using quite an old-fashioned formatting of decimal places there, average of the 10, our standard deviation, min and max. So let's run that. So I just reset it because I got an error because I hadn't actually run the cells with the methods in random choice. Okay, now we set our environment. And now each of these is sort of running 10 times, just randomly poking it until it goes 15 degrees off the vertical. And we see we got an average of 24 steps before it fell over, standard deviation 8.7, minimum 40, and a minimum 14, maximum 40. So that's an example of using that environment. Now let's create a very simple policy. Policies don't have to be learnt, don't have to be deep learning. Our basic policy is that if the pole starts leaning to the right, we'll poke the cart in the other direction. So we're always going to be poking the cart in the opposite direction to which the pole is leaning, which seems a reasonably sensible first policy. So our policy is how to convert actions, how to convert state observations into actions. So we pass the observations, and CartPole observation gives us 4 things. We have where it is, the position on the track, its velocity on the track that it's currently going, the angle that the stick is at, and the angular velocity, how fast is it falling in one direction or the other. So to get our angle, it's observation index 2, because 0 position would be 0, x position would be 0, velocity 1, angle 2. And we're going to return action 0 if the angle is less than 0, else 1. So that's our basic policy. So let's run that again. And again we'll see it sort of trying. It's going to run it 10 times. Now our average, we got 39 steps. Standard deviation of 5.6, a minimum 31 and 53. So our simple policy definitely looks like it's doing better than our random policy. So random actions is always a good place to start just as a policy, gives you a basic benchmark. Then if there's something that you think you can reasonably code to create a simple non-learning policy, you can try that. And then what we're now going to go on to is a double deep Q network. So I'm going to pause here. Okay, so I'm going to open up CartPole DDQN, double deep Q network. Right, and this includes some introduction to reinforcement learning and deep learning, which we went through before, but you've also got it here as a notebook. The PDF of the slides will also be in the GitHub repository, but it's also here. Now, we'll go through this slowly. The next one will be applying this to the hospital model. But it will essentially be the same as this. So we'll go through this slowly, and then we'll show how you can bring in and just slip in a different type of model using the same learning environment. So we have our information about what reinforcement learning involves, which we went through before, some definitions of elements of reinforcement learning. So these are the way people use those words. A bit more about types of model, which I didn't go through. So types of model, you may remember this from Lex's video that we watched on deep reinforcement learning. Model-based means you actually have a model of the environment that you can test things out on. So you might have a board game that's kind of simulated. Now, most reinforcement learning is what's called model-free. And that's where you don't have a model of the environment that you are using to make decisions. In our hospital bed model, we have a model of the environment, but the Deep Q network never has direct access to it. It just gets observations from that simulated environment. It can never probe that simulated environment directly. Then we have policy-based methods, which go straight to deciding what's the best action to take without trying to calculate any value, which we haven't spoken about today. And then we have value-based methods, which are based around estimating a value of either a state or an action from a state. And we're doing Q, deep Q learning. It's a value-based method. It's a model-free, value-based, and the value we're looking at is the reward that we'll get from a particular action. Then there's off-policy and on-policy. Off-policy, they can learn from historic data, so you can sample what's gone on in the past and learn from that. On-policy requires active learning in the current environment, and you've got no historic database to sample from. Right, DQ networks for reinforcement learning. So here's a very simple schematic. That we have our state observations, and for CartPole we have just got 4, which we saw. It's the position, the x position, the x velocity, the angle, and the angular velocity. We'll have a look in the hospital simulated environment, what we've got there, it's a simpler input, if I seem to remember, but I can't remember at the moment. That goes into the policy network, so standard neural network stuff, and it outputs, this is our X, this is our Y, and our Y is the estimated Q for each action. And then we take the action with the greatest Q. And then a reminder that Q is learned through the Bellman equation, so the Q for any state action pair equals the immediate reward plus gamma, our discount rate, multiplied by the best Q of the next action or the next state that we end up in. So key components of deep Q learning, or it's actually double deep Q. So we can talk about our agent, and that's what interacts with the environment, and it needs to learn the policy. It's also the thing that will have the memory. So some of these are a bit overlapping, but the agent is kind of that which is learning. Then we have our environment, which is the model of the world. So our interaction is between the agent and the environment. Components of the agent that we talk about and we'll set up is a memory. So that's a database of state, action, reward, and new state. So S, A, R, S prime, and whether it's terminal state or not. Then we have our policy network, and we use that to decide what action we're going to take, assuming we're not using random exploration. And then our target network is the name we gave to the reference network we only ever use in training to get the predicted Q for S prime, A prime, the next state you end up in, and the action with the best Q. You actually decide from the policy network, but you get its Q value from the target network, and that's a trick used to help stabilize. And it's a bit of a shame we need it in there, but we do. Okay, so now the general method of Q learning, and this is kind of repeating what we had before, but it's reiterating in the notebook. I'm going to go through it again now just so help drill it into your brain. So we start off with an observation from the environment, and we pass that to the policy network, and that returns a preferred action, and the action is whichever action creates the highest or leads to the highest estimated Q, our long-term reward. But we may also just take an action at random, and we reduce the probability of taking it random with time. So we pass the action to the environment, and the environment returns what's the new state, S prime, what the reward is, and what's the terminal, whether there's a terminal state or not, and then a dictionary of any extra information. That's standard in GIM, but we're not using it here. In fact, it's empty here. So we know S, we decide on A, and the environment returns R and S prime. And then we store those as a transition state in memory. What state was I in? What action did I take? What state did I end up in? What reward did I get? Was it a terminal state? And then each game step, we update the policy network. And we'll talk through that briefly below. And then every so often, perhaps every 1,000 steps, we update our target network simply by copying across the policy network. So our target network is a stable but increasingly outdated version of our policy network. Initially we might have pure random exploration, so you choose an action at random, pass that action in the environment, and then again we just store that in memory. So our first, however, training steps in the environment are all random, but the memory doesn't know that. It just knows the state, the action taken, the reward, the new state, and whether it was terminal or not. Okay, so this is what we went through before, so I'll only go through it briefly. When we train our network, when we start training, when the memory's reached our required size, we take sample from the memory, and we'll actually do this about, I think, 3 or 5 times per game step. And then we get the value of the best of the new state from the target network. Now we've actually used the policy network to decide what action it's going to take from the next from the next state S prime. So all this is being used to update using our Bellman equation, updating Q. So our policy network returns Q for each action that we could take, and the point of training it is to update that Q and get a more accurate measurement. So we've got our reward, we can calculate a target Q by the reward which we know about, and then we get the max Q from the target network. That creates a new target Q for the policy network, and we train our policy network on the target Q for that state and action pair. And so the next time we ask that network what the Q for that state action pair would be, it's closer to this target. And then every 1,000 steps or so we copy across our policy network to our target network. It's a reference for deep reinforcement learning with double deep Q there if you wanted to look at the paper. Right, now when we go through the code, I will point out some things in Python, but the main thing I'd say is look at the structure, because this structure is common to all reinforcement or nearly all reinforcement learning. If it's going to vary, it'll only vary a bit. So what I've put here is the structure of the code with numbers, and you will find as we go through the code those same numbers in the code, so you can find those bits there. But let's quickly run through this. So as ever, we import our packages, we define some standard model parameters which we'll see. We'll create a method for creating our DQ network class for both policy and target. It's the same network definition. We define a policy net training function, so that how to optimize the policy net. We define a memory class. We define a plotting function here to plot just how well we did. And then we enter our main program where we set up our environment. So in the first case this is going to be gym, later on it will be a hospital. We set up our policy and target nets using the function we defined earlier. We set up our memory using the function we defined earlier. And then we start a training loop. And we're going to train for, we could either say I want you to train for 100 episodes, and then we might look at our training curve and see has it plateaued, do we want to carry on training? Or in this case it's going to carry on training until we break it. We break the training when we've reached an engine that can do 200 steps on the CartPole, keep it upright for 200 steps. As soon as it hits that for the first time, in this example we stop training. Optimal training would probably carry on a bit further to make sure it's reproducibly can achieve that goal. Though if you overtrain, you can lead to instability again. So when looking at these sort of methods, we might want to save our model when it's kind of at its best, because overtraining reinforcement learning can lead to problems. So our training loop is we reset the game. When we play an episode, we reset the game, and then we have a loop within the game, which is each step of pushing the pole in this case. And we get our action from our policy net based on the observations. We play our action, and then that returns new state, reward, and whether it's terminal, and we add that to the memory. Remember, we're not training on things that we immediately discover. Then it's going to just check, have I reached the end? Is it a terminal state? Or and then it's going to update the policy net with the steps we outlined above, and then go back and repeat that, get an action. And it's going to carry on that loop, though every 1,000 steps or so, I think it's 1,000 in this, we have a look, it's going to update the target net by simply copying all of the weights that are in the policy net across to the target net. Okay, so that's the structure of the code, and that will be identical when we run our hospital. Currently looking, not going to show you, currently looking at an engine that can help locate ambulances in the optimal location if they've dropped a patient off. That could also be dependent on where other ambulances are, and it will follow exactly this structure. It will be pretty much identical, but with a different problem setting. Now that's the beauty of these methods. So let's have a look. Import our packages. Nothing particularly exciting there. We're using PyTorch for our neural net framework. On Titanic we used TensorFlow. PyTorch, it's similar. There are some things that are a bit easier or quicker to do in TensorFlow, though I think PyTorch is often easier to understand. What it requires more lines, but it's kind of more explicit in what it's doing. For reinforcement learning, it's also a lot faster. This slightly peculiar thing where we're kind of hitting the network for just updating one at a time or getting one thing back at a time. PyTorch is good for. TensorFlow's designed for big bulks of data more. From collections import, this is a double-ended queue, which we're going to use for our memory. It's a convenient thing if you want to, say, keep 1,000 of the last memories. The double-ended queue will automatically forget the oldest when it's reached 1,000. So we kind of push it in one end of the queue, and if the queue is full, it drops out the bottom, and we're going to use that as a memory. Right, define model parameters. We've got our environment name. Display on screen while it's training. We'll show it at the end, but while it's training we don't want to be showing it because that would just slow it down enormously. Here's our gamma from the Bellman equation. So these are things that you can try adjusting, and I'd encourage you to do it on this. What's the difference between gamma of 0.8, 0.9, or go up to 0.99 and see, does it make any difference? This is the learning rate of the network, how much the network is updated in each step, so you might want to adjust that. Probably don't go above 0.01, but you could go down slower, in which case the network will update less each time, but it might lead to a more stable network. It might lead to smoother learning. Memory size, we can store up to 10,000 steps and then it will start forgetting. So this is the sort of thing that, do you want your memory to be huge, or do you worry that old memories aren't as good for training on? And you can adjust the memory size here. The batch size, so this batch size is 10. This means it's going to update the policy network with 10 samples from the memory for each game step. Sync target steps. I was mentioning sync every 1,000. This is actually set at 300. So every 300 steps, it will copy across the network, the policy network weights to the target network weights. Replay start size is how many random steps do you play and feed into the memory before you start training the network and sometimes using the network to pick the action, and you'll use it more as time goes on. And the latter is defined by the exploration rate. Epsilon is the probability of choosing a random action, and this kicks in after we've started with our replay start size. So we fill up the memory with 500 random steps, and at that point we start training the network, and our epsilon, which is the probability of picking a random action, decays with each step. And we start off with a 100% probability of picking a random action, and we go down to a 0.01, so effectively 0. You could set it to 0, or you could say maybe you get more effective learning if you always, I don't know, had a 10% chance that you picked it at random, 5%. This goes down to it'll choose very few actions randomly. And then our exploration decay, each step we multiply our exploration rate by 0.995, and so this reduces our epsilon, the probability of picking an action purely at random with each step. And again, if you wanted to decay more slowly, you could have, well, let's go for 0.999. Well, we'll see what that does. And then we've put our target reward of 200. So if you do a run that gets to 200, in the way we framed it here, you stop training immediately. You could say I want to hit target reward 3 times in a row or 5 times in a row if you wanted to make sure this thing is consistent. You change your code a bit for that. Okay. Now let's define our DeepQ network. And I'm not going to go too much into all of this. I'll just pick out a few things. You remember from your Titanic, we define a number of layers. First of all, we call it a DQN class, and NN module we imported back up in the imports. That's the standard PyTorch neural network class, so it's inheriting from that. We're going to store the exploration rate in this object. So this object's more than the network. It's containing some what we might call metadata around that network as well, what our exploration rate is. Our action space we pass to it, which is how many actions are possible. So if there are 2 actions possible, we want a neural network that outputs 2 values, 2 key values. So when we're defining the network, we define our observation space, the number of features that will feed into it, our action space, and the neurons per layer, 24. So you remember in Titanic we could vary both the layers and the neurons per layer. Here the only thing you can put in is neurons per layer. Memory we set up as our double-ended queue, so this is in our DQN object, and here's the neural net. That's it. That's our DeepQ network. Of all the lines of code, that is our agent, and it's going to make so it's going to inherit properties from the parent class. And it's a sequential, just like in the Titanic, and there's 2 hidden layers. The first one takes the observation, and then we have a layer of 24 neurons. The second one, it takes the output 24 and passes it to another layer of 24, so that's our second neuron layer, hidden neuron layer, and then it goes down to our action space. So if we've got 2 actions, then we can we'll have 2 outputs here. So you can use this for any number of observations, any number of actions. You can change the number of neurons. You could put a loop in there to create, just like we did with Titanic, you could create any number of layers if you wanted to build. Even though DeepQ learning is called DeepQ, very deep networks are rare in DeepQ learning, unless you've got to navigate a very complex path through something. Then you might have a very deep network, or a reasonably deep network. Then we define what's going to be our objective function for calculating our loss, and we covered this last time. This is mean squared error loss, which is the standard loss that you use for when you're predicting a value rather than a category. If you're looking at a category, then you would use a cross entropy loss. So even though we're picking an action, you might think, well, that's a category you're trying to classify. The neural network itself is predicting a value, which is the Q of each action. So for that, we use mean squared error loss. Remember, we tend to use either mean square error loss if you're predicting a value, or cross entropy if you're predicting probability of being a member of a given class. Then our optimizer, we use Adam, which we mentioned was, is a very good first start for everything. If in doubt, pick Adam. And this is in PyTorch just how we set up Adam. You always say parameters equals self.net parameters, and then we pass its learning rate as well, which we had up in the definition. Then we've got an ACT method as part of this network, and because it knows the exploration rate, it will choose, it picks a random number between 0 and 1. If that's less than the exploration rate, it returns a random number in the anywhere depending on the number of actions. So if we've got 2 actions, it will randomly pick 0 or 1. Otherwise, it's going to choose the best predicted outcome. And Q values, this is how we get the Q values out from, we pass it the state and we get the Q values, and then our action is the greatest value of those. But we have to do this slight trick here, which is to detach it from the neural net. Don't worry too much about that now, apart from knowing you've got to detach it from the neural net, and you convert to a NumPy array. And this 0 is just because the network can predict 10, you could pass it 10 actions in 10 states and it would send back 10 sets of answers. We just want the first one because we're actually only passing it one set of actions, but we still, the way it's framed, we still need to say, well, show me the first set of actions from the predictions. And then the forward is, we'll come back to so the forward is just returning, when you pass an X, it returns the Y. It's just a way of getting the prediction out, which we use up here, self.net. Will automatically call the forward function. Forward in neural networks is just, I'm giving it X and I want Y. Okay, so that's our network. Now is our training, and I'm not going to go through this in detail at all, apart from to say this is the bit that is getting the predicted values out of the network, getting the predicted values for the next state out of the target network, and then creating a target queue based on the reward and the Q values from the target network, and then it is updating the neural net. So this block here is just creating the new target values that you're going to train on, and we only ever replace, for each state the neural network will output, say, well, in our case, two Q values for actions 0 and 1. We only update one of those actions at any one time, which is the action we took. So all this is the bit that we were talking about. You can work through it slowly, getting those values and creating the expected state values is the target queue that we want to train our network on. The 2 bits here are just if you're not in a terminal state, or if you are in a terminal state, Q is simply the reward that you get on the way to the terminal state, and there is no gamma Q argmax for the next state, because terminal has no Q. And then this bit is neural network updating. So this is, you'll see the syntax is a bit different to the TensorFlow example, but you'll see the steps are essentially identical. Here we specifically have to have this zero the gradients in the network first. Don't worry too much about that. PyTorch, you need to explicitly just zero the gradients. You calculate a loss, so the loss is the difference between state action values, which is what the network has outputted, and expected state action values, which is our target value. So if this was in a normal neural network, we might call that predicted Y, and that actual Y, or label, or something like that. Then you back propagate the loss. You might remember what that does is apportion the loss through saying how much does each weight in the network contribute towards the loss, and then we call the optimizer, PolicyNet optimizer, dot step method updates the weights in the network. So this is the PyTorch method of updating the network. Zero the gradients, how much, so the gradients in the network is how much does the output change as you change each weight. Calculate the loss, what's the error, what's the difference between what I predicted and what it should be. Back propagate that loss through the network and update the weights using the optimizer, which is Adam. Okay, here's our memory. So we define a class for memory, our constructor, and it's simply self.memory is a double-ended queue, and we pass its maximum length, memory size, the number of observations it will keep before it starts forgetting older ones. And then our only method is remember, and we pass it state, action, reward, next state, done, terminal. And then we add that append. So it's like dealing with a list. We wrap that in a tuple, so that's why there are two double brackets there. The inner one is create a tuple out of state, action, reward, next state, done, and append it. And the double-ended queue method, it will automatically drop the oldest one once it's gone over the memory size with append, so we don't need to worry about losing old items. It will do that automatically. Okay, just our plotting function here. We're going to plot our exploration rate and our score. So standard matplotlib type syntax there. Now on to our main program loop. So we set up our environment, and there's a gym.make method with our environment name. Our environment name we set up at the beginning. Let me go up to that. CartPole version 0. So let me just go back down again. Sorry about all the scrolling on the screen. Hate it when people do that. So this is going to make a CartPole environment. There are dozens of environments in Gym, so we could say make. There's one, for example, called Frozen Lake, where you have to kind of navigate around a lake, but you might fall in a hole. And you might remember Lex talked about similar things, that you might, even though you might walk forward when the hole is to the right, because it's frozen, you might slip and fall in the hole. So depending on how you deal with rewards, you might choose to take the shortest route, or you might choose to take a longer route away from the hole. So that makes the environment. Observation space. This is just a Gym method that tells us, well, how many observations are we going to get out? We know there are 4, but if we're using a different environment, this will pull it out automatically. So our 4 observations are the park hole x, x velocity, pole angle, pole angular velocity. And similarly, we can get how many actions with this syntax n for action space .n just tells us how many possible actions. And so our observation space and action space define how big our inputs for the neural net need to be and how many outputs we have. So we set up our two nets, our policy net and our target net, using the method we defined earlier. And then we copy our weights. So we set them up as, so they're two different networks in memory, but then we copy our policy net weights across to the target net. So the weights are what turns the input to the output. So our policy network and our target network start off identical. Now we're going to set our target network to what's called evaluation mode. It just means that PyTorch handles it in a slightly different way. It knows it's never going to need to update that network, and it keeps it faster. I guess that's the main thing for this. It keeps it faster because it knows it's not training. We set up our memory. Then we're going to start our training loop. We're going to sort of just a run counter here, and all steps will keep a record of between episodes, so that's used to decide when to update the target network. Set up a couple of lists for each episode of the game, which is either if it gets to 200 or the pole goes more than 15 degrees off vertical, it will stop. We'll set those up as an exploration list to record exploration rate at that point and what the score was. And now we start our learning, and our learning is a continual loop. So continual loop is true, while continue learning, keep looping, basically until we force a break. So rather than a for however number of times, it'll keep doing this until we force a break in the loop. Increment run. Set up our environment. Now when we set up or reset our environment, we get our first state observations back. So we could call that state, or we could call it obs. We just need to reshape those a little. Don't worry too much about that. This is just to put it in the right format for passing it to the PyTorch network. And it's just because PyTorch and TensorFlow normally expect a range of X cases to be passed to them in one go, rather than sort of saying, here's an example of a range of X features, give me Y. Both PyTorch and TensorFlow are basically set up to take an array of multiple examples of X, and that's called a tensor, and then return multiple Y's. And this just puts it in there, it just adds a dimension to it, basically, so that it can find the observations properly. Reset our step count, and then while true we've got another continuous loop. So this is now a game episode that's going to continue until the pole has fallen over. Increment our steps and our all step counter. Display on screen is whether you want to show it moving around, but most of the time you don't while it's training. So action, we pass our state to policynet.act, and so that puts state as the input to the network, and that action got the predicted Q from the network, and then it also found which is maximum and returned the index of which is maximum, the argmax. So we pass that action to the environment just as we did with CartPole before, and that will automatically, whenever we pass an action to the environment, we'll get the next state, the reward, the terminal, whether it's terminal or not, and info. We can update the screen if we want to. We're not going to want to most of the time. And then our reward, the way CartPole returns reward is that it's always 1. what we do is we'll keep it at 1 if you're not terminal. If you are terminal, which means you've kind of fallen over, then set it to minus reward, so -1. So that's just something we need to do for CartPole, because we know it's always returning 1. If it's actually fallen over, we want to change that reward to -1. That's a bad reward to have. Then our state next came out of our step action, and again we just reshape that for PyTorch, and it would be the same if you were using TensorFlow. You could use TensorFlow and you'd still want to reshape it in this way. It just nests that one observation, set of observations, inside a bigger tensor, a multiple dimension array that could hold multiple sets of observations, but we're just holding 1. Then, so we've got our state, our action, reward, state next and terminal, and we've converted those to PyTorch friendly versions already, and we call our memory to remember it. And then our state, current state, becomes what was returned as our next state. So we've got a particular state, we decide on an action, we pass it to the environment, and it passes back the new state, which we called state next, and now we set our current state to be that new state next. It's now going to look for the end of the game episode. So that's going to happen if it's fallen over or if it's reached 200. CartPole will automatically truncate it at 200 steps. This just prints stuff out around what the run is, what's the explanation, what's the score. This guff up here, this is actually just keeping it all on one line rather than printing on multiple lines. It's simply, the R is to go back to the beginning of the line and print what's called clear line is 80 spaces. And then when it prints which run number, again it goes back to the beginning of the line. So this stuff looks complicated, it's just to clear the line and print in the same place each time. And then we're going to keep our exploration rate and keep our score as we've gone through. Then if we've reached our target reward, continue learning equals false. So we had at the beginning while continue learning, which is normally set to true. We set that to false if you've found the reward, or if you've got to 200, say, and then it will stop going through more episodes. And then end the current episode if we've reached a terminal state with break. So that was just all if it was terminal. Normally we're sort of, most of the time it won't be that, and we carry on, we update our policy net. I mean, we do that even if it's a terminal state as well. We update our policy net unless our memory isn't big enough, in which case we use continue. So this is, we said, a replay start size. You have to produce a certain number of steps before you start learning. So if our memory length isn't up to the replay start size, we continue. So this continue goes back and carries on round the loop, ignoring anything after the continue. Otherwise we want to update our policy net, and this is where we call the optimize, and we pass it the policy net, we pass it the target net, which isn't updated at this point. The target net is just used to get the predicted queue from actions from the net for the next state, and we pass it a memory that it's going to sample from to update. And then we update the target net periodically. So this is our all step counter. So basically if that divided by sync target steps has no remainder, So if all steps is exactly divisible by sync target steps with nothing left over, then update the target net by loading the state net dictionary, which is all the weights, over the target net. So it's basically making a copy of the target net. So let's, I see an old one's hanging there, let's run that cell. Name Jim is not defined, that's because I haven't actually gone through this, so let's kernel, restart, clear output, kernel, restart, and run all cells, and we should see it running. Here are the runs. Here's our exploration rate, the probability that we're choosing an action at random, and our current score for the last episode, and we should see that slowly go up. And even though we're taking random actions, because I put a very slow gamma on here, it's actually already, even though it's randomly acting still 1 in every 3 turns, it's managed to get up to 200. Let me just go back and change that decay rate. So that was exploration decay I had at 0. I changed to 0.999. Let's change it to 0.9. You can try changing these things and see how long it takes to get to 200. So now it's running again. Our exploration rate's dropped much faster. It may be worse, we'll see. If it's deciding too early to always follow the net, but it's done all right. It suddenly seemed to, so the green is the exploration rate, so this is the bit that while we're accumulating memory, we say don't start training before the memory reaches this size. Then our exploration rate decays quite rapidly here. Here's the performance, so the performance is still low, presumably while it's learning, and then suddenly it seems to get a lot better. It's suddenly learned. This next one runs the model 10 times just to say, well, was this a fluke? And this is why you might want to sort of see that it's consistently good, but actually averaged 194, minimum was 150, maximum was 200. When you ran that trained model 10 times, basically it's performing pretty well every single time. That's what this loop does. It's simply going up to 200, so we're going to run 10 episodes. Each time we reset the episode reward, we reset the environment, we do 200 steps, we get the observations, reshape it into a PyTorch friendly format, get the action from the policy net, pass that action to the environment with step, and that returns the observations, the reward, done, terminal, and any info, and our episode reward, we plus our reward, and if we're finished we break, and then our totals list of the 10, we just append our episode reward to that and then close the environment. And then finally, if we want to, we can watch one. This is going to render one of them, so display it, which you might have seen it came up, but let's do that again. And we can see now it's keeping it much more steady. Towards the end it seems to be moving faster, but CartPole stops at 200 rather than sort of saying, can I keep it kind of infinitely long there? So if we start that again, because the environment reset will start it, and perhaps in a slightly different movement, might look a bit different. There we go. It's gone off the other side then slowly. So that's a DQ network. So we'll come back and we won't go through all of that again, you'll be pleased to know. Have a look through it though in your own time whenever you want to, because remember these numbers here correspond to the code outline here. That's a slightly more detailed version of the things that are described up here. So that's the basic method, and then it's broken down more in the code steps. So have a look at the structure of the code, because that's the DQ network, which should be useful for all sorts of things. Because remember, the DQ network, we've just got a 2-layer one. You could build bigger, more complicated ones to learn more complicated connections between what the state is and what the predicted long-term reward Q is. Okay, so have a break and we'll come back and have a look at the hospital model. Okay, last bit. Let's look at the agent learning to control beds in a hospital simulation. And we'll have a brief look at the simulation in a bit. We're not going to spend any time at all really on the agent-based learning side, because as you scroll down through it, you will see it is identical. The only thing that changes at all significantly is the plotting the results, because we want to plot some results specific to this simulation. All of the rest, the setting up of the networks, the looping through, choosing actions, getting reward, learning, is all exactly the same as CartPole. So we've gone from CartPole to a whole hospital model while keeping the structure the same. A more complex problem would probably need a bigger network, but we can change that. We can change the neurons in the network. We could add more layers. We could make that adjustable. But it's essentially the same, because what we're doing is the same in that we're feeding a network input values, our observations X, and what we're getting it to learn is the predicted Q of each of the actions from Y. And we have the same method of updating that network, that we're getting rewards from the simulation depending on how we're doing. We store that action, state, action, new state, reward, whether it's terminal or not, in memory, and update just as before. So we go from a simple control system to a system that needs potentially more complex control, and it's exactly the same structure. So let's describe what this hospital model is, and it's very simplified. This isn't supposed to be a hyper-real hospital simulation. It's to show in principle that these methods can interface with each other, that we can make AI agents that interface with our SimPy type models of healthcare systems. So we have a default arrivals, 50 a day, but weekend arrivals are half that, and weekday arrivals are 120% that. So we got 60 arrivals during Monday to Friday, 25 arrivals on average Saturday and Sunday. Inverse exponential distribution, Dan's probably covered that on the SimPy course. Average length of stay is 7 days by default. All this is variable. Length of stay again is inverse exponential in this. The reinforcement learning agent has one opportunity a day to ask for change in beds. It can request, it's got 5 discrete actions. It can ask for a drop of -20 staffed beds. It can ask for a drop of -10, stay the same, add 10 or add 20 staffed beds. But the bed changes take 2 days to occur. That's both the staffing or removing of staff. So we've got a bit of a delay that it's got to learn to cope with. We can put in a target proportion of beds that are free. Beyond that, the reinforcement learning receives a reward based on the number of free beds or number of patients without a bed. So once you go above the target reserve, for every bed that doesn't have a patient in, it's penalised. You get a score of -1. Once you're below the target reserve, every patient that doesn't have a bed is penalised by -1. And so it's almost impossible to get it exactly right. So just like in the real world, you've got doctors who hate having patients with no beds, and you've got accountants who hate having lots of beds without patients, and you're kind of stuck between the devil and the deep blue sea with those competing objectives. And it's trying to find a balance between what's the balance between those that achieves the best reward as we define it. We load the simulation with the average number of patients present. So the rest of this is basically the same. So let's open up the sim. So the sim is in simulated environments, and it's in simple hospital bed 1. Just to describe basically the structure, because we can build any SimPy simulation or MESA simulation to act in this way if we want to. Any environment needs a way of monitoring its state space, which is what we get the observations from. So it's, you know, what is the state of the environment at any one time. We need to decide on a reward structure, and that can be really important. We need a reset method that returns the first set of observations. We need a choice of actions. We need to make sure whether the action is legal and possible before we break the simulation. And then we have a step method that passes the action to the environment, and then it returns the new state, the reward, whether the state is terminal, any additional information in the dictionary. We want a method to render the environment, show it in some way, and a way to recognise a terminal state at the end of the episode. So for the bed 1, it returns a terminal state when the simulation has reached its desired endpoint. The way this is structured is we have a whole lot of internal methods, things like calculating reward, checking it's legal, and you'll notice each of those begin with an underscore, which kind of is Python sort of code saying, look, this should never be called from outside. You can call it, but you shouldn't normally. And then we have interfacing methods, which are methods that are designed to be called from outside. So we have a rendered method for displaying the state. We have a reset method which initializes the environment and returns the first set of observations, and a step, take an action, update the state, return observations for the new state, reward, terminal info. Should all feel pretty familiar now, just like CartPole, just like what we were talking about in the initial tutorial several hours or days ago, that it seemed. Anyway. And then we have various parameters around the model arrivals per day. You can change the delay to change beds, it's 2 days. What if it took longer? Change the length of stay, how long the simulation is going to run for, things like that. So I won't go into it, but you can see going down here, it is hopefully a reasonably well described model, which is what we would normally try and achieve. That we describe what the methods are, we comment throughout, and then we have our internal methods starting with underscore, and our interfacing methods with no underscore. You would only make that distinction if you have interface and non-interfacing methods. Sometimes you don't, but for us it's obvious. We've got an agent that is going to call one of 3 methods, reset, render, or act. And so the methods describe what's going on. So you can look at these in more detail if you're interested in a hospital bed simulation. It's very artificially simple. Okay, so let's go back and let's run this. So we've got our 5 discrete actions. So compared to CartPole, we've got a different set of input number of features. We've got a different set of actions. We've got 5 now rather than 2, but it copes with all of that. So I'm going to run it. Then I'll just pause it while it runs. I think it's going to do 250 training episodes, which is way more than enough. But we'll run it. Restart run all. Oh. And we see at the bottom that it's just telling us what the run is, what the current exploration rate, that's the probability of picking things at random, what the average reward is. So I'll pause this, let that run. Okay, that's completed. So on the left hand side we see the green line is the exploration, which drops down quickly to 0 on this first one, and the red is the performance, which initially gets worse, particularly as exploration is reduced, and then it picks up and stabilizes. And on the right we have the number of, this is just the last run, the number of patients in hospital. The red, that's what it's trying to cope with, and the green are the staffing decisions, bed staffing decisions it's making. And so we've got an overall occupancy here of 92%. 59 days were under capacity, 304 days were over capacity. But we weren't over capacity too much because we have an average number of patients 497, average number of beds of 539. So, and that's an example. The key thing is we've taken a generic deep Q network, double deep Q network, and we've taken it from CartPole and we've transferred that to this type of hospital simulation or healthcare simulation that we do, by designing the hospital simulation with the same interface methods as GIM, which allows us to just take agents from one place and pop them in another, and then because after that it's the same, which is really nice. So that's an example. Now I'll link through in the video description, there'll be the GitHub repository for this code, also GitHub repository for a range of different alternatives, refinements of double deep Q. So this really is the baseline deep AI, deep learning, artificial intelligent agent, if you like. Nobody uses DQ learning without the target network. That's what gives us the double deep Q. Double deep Q is the sort of basic method, and from there are various refinements to improve performance, make them more stable, such like that, give more, rather than always coming up with this is the one action, say giving a probability distribution over different actions that you might take, so sort of certainty around how certain are you in the action you want to take. So I hope you enjoyed that. This is a bit of a technical one, this one, and to getting to grips with Q and then DQ networks, and then unfortunately we have to have this target extra network on it. It'd be nicer to sort of explain these things without that extra complication, but it is needed for anything remotely usable. But with that modification, you can see it. You can theoretically put this into all sorts of environments. You can make the learning network as big as you want to learn more complex patterns between input features and Q value. So it looks like it's going to be a very powerful method that we'll be exploring more. So if anybody's interested in this, do get in touch with me, because we're always keen to talk about this stuff and think through where might it be useful and such like. So that's m.allen@exeter.ac.uk if you want to get in touch. Great. I hope you found it okay and not too head spinning. Though yeah, it's not an easy one, this, when you first come across it. It's quite a few things to fit in your brain in quite a short period of time. So you have my sympathy. It drove me nuts for a while, this, until I started using it enough to everything. Then you just get kind of so familiar with it. But I know it's not easy to begin with. So hope that was okay, and see you around.